Hello, everyone, and welcome to this RFMW and Marki Microwave webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenter. With us today, we have Harley Berman. Harley is an Applications Engineering Manager with Marki Microwave. Harley, welcome to today's event. And with that, I'd like to pass things over to you to get us started.
Hello, everybody, and welcome to today's session. We're going to walk through Marki's new suite of online tools and see how they can help you accelerate your design flow and help you find the right components faster with less hassle. But before we dive in, I'd like to take a moment and thank RFMW for co-sponsoring this webinar, and also a big thank you to Katie and the Global Spec team for hosting today's webinar. Now, as Katie mentioned, my name is Harley Berman, and I am the Applications Engineering Manager here at Marki Microwave. And a big part of my role and the role of an applications engineer at Marki Microwave is helping our customers solve tough RF design problems. Whether that's integrating our parts into a larger system, figuring out which product is the best fit for your given specs, or troubleshooting some unexpected performance. Whenever we do this, whenever we're working with you on these types of problems, we internally rely very heavily on some free, easy to use tools that we have built right into our website. And today I'm very excited to show you exactly what's available and when to use each tool, as well as kind of just discuss how these tools really do make design processes faster and smoother. So let's get started. Again, big thanks to RFMW for the co-sponsorship. And we'll start with just a sort of general understanding, which is finding the right part can be very tedious. Personally, I know from experience how difficult and sometimes just frustrating it can be to comb through stacks and stacks of data sheets like the engineer here, trying to figure out the best LNA, mixer, or filter for your system. What you end up doing often is you're bouncing between plots and tables and specs. You're hunting for tiny differences from part to part that could make or break your design. And then after all of that analysis, and you think you found the right part on paper, you still have the trouble of figuring out how it'll actually perform in your system with your unique frequency plan, your operating conditions, your bias, temperature, what have you. That sort of process alone can give anyone a headache, and we've all dealt with it. So today, we're going to take a very simple design example, and we're going to walk through exactly how to tackle these challenges by utilizing the full suite of tools that Marki applications engineers use on a daily basis. So let's take a look at a typical signal chain we might be designing for, and I'll show you which tools are at your disposal to help you with every step along the way. So here is a very simple receiver that you might be tasked with designing. So pretty common stuff. We've got an antenna, which is feeding a limiter to protect your front end. Then an LNA, which is going to boost your signal. There's a higher frequency channel selection filter, which feeds the mixer, which is used to down convert the entire spectrum to some low frequency IF, which is filtered out and cleaned up before getting into your ADC. Here I'm showing an active solution, a single-ended to differential amplifier, but this could be, passive balun, what have you. On the LO side down here, I've made it very simple. It's just a high-frequency driver amplifier that's feeding a mixer's high-frequency LO port. Now in real life, each of these blocks, the physical component that we choose, has design trade-offs that affect the greater system. So the parts you choose matter. So for example, the technology of your pre-select filter is likely totally different, or it could be totally different from your IF filter. The performance of the LO generation chain, both this amplifier, and you may have a more complex, multiplier chain here or something like that. The way you generate and feed your LO into your amplifier, into your mixer, has a direct impact on mixer spurs. Those spurs are going to affect your dynamic range. That might cause you to change your entire frequency plan, for example. These types of problems are the types of problems that our online tools are designed to solve quickly. And the goal is so that you, as the design engineer, are not spending days or even hours buried in data sheets. You can quickly search the entire Marki catalog. You can quickly design custom filters or compare specs side by side, even run quick high-level simulations to see how parts interact with your system, all using free online tools. And I really do mean free online tool. You don't need to download anything. If you have an internet connection, you can use the tools we're going to talk about today. Now, just a quick moment to mention, if you're interested in how to design and model receivers like this, I've actually done a couple of webinars focused on just those topics. They're linked in the sidebar, so definitely check those out if you haven't. But today's session is not a design session. We're not going to talk about how to design a receiver. This is all about the tools we use to pick parts fast, to compare options, and model these system level trade-offs before you ever build hardware. So with this receiver chain as our example, I'm going to show you what tools are at your disposal, how they work, and then a couple of quick tips on how to get the most out of them. So let's get started. To make this easy, we can loosely group all of Marki's online tools into 4 main categories. We have filter design tools, or really just filter tools. We have system design and simulation tools. We have product comparison tools, and then just a collection of handy utilities and conversion type tools that are just useful for the RF engineer to have at their disposal. We're first going to talk about specifically what tools are available in each category, and then we're going to pop over to the Marki website for a live demo of each tool that we offer. So first up, let's talk about our filter tools. For the design example that we're using, these are going to help you tackle the front end and IF filter design challenges. When you design a new receiver, such as this one in the corner, your first step as far as filters go is typically going to be to see what's already available off the shelf. Since these off the shelf parts, they're quick to get, they're already fully measured and validated, and you avoid any sort of lead time or NRE costs that come with custom designs. Now, the challenge with catalog filters is that digging through a huge catalog of hundreds and hundreds of filters can be just like painful without the right interface. So to combat this problem, we developed our filter search tool to make that fast and easy. With this tool, you can instantly filter down hundreds of parts by key specs. You can easily overplot multiple responses and see at a glance which filters come close to the ideal requirements we're hunting for. And right down to giving you like a percent match and overplotting as many or as few filters as you want to see for just quick comparisons. And this is great. This tool quite literally is used on a daily basis by the applications engineering team here. But as you know, when you're designing a system, you can't always use off-the-shelf filters because of the nature of filters. They're often highly specified and highly specialized for their given application. And sometimes there just is no perfect off-the-shelf match. Maybe you need, slightly different passband shifted a couple hundred megahertz away, or you need tighter rejections, whatever it is. That's where our filter design tools come in. We offer easy to use LC and microstrip filter designers. These are great for low frequency and or quick idealized prototypes, plus a fully validated mimic filter design tool if you want to see what's possible on monolithic designs. Now, this Prodigy filter design tool has been the subject of a couple of past webinars, which we'll also link. If you want to see, a deep dive into how our mimic filter design tool works and a couple of examples and caveats. Now, in today's webinar, we're going to have a live demo section as well, and I'll show exactly where to find these tools, how to use them, and the trade-offs between the different design tools we have. But before we get there, before we jump into the live demo, let's take a look at the next set of tools, which is our product comparison tools. The product comparison tools are designed to help you make part selections quick, easy, and smart part selections by comparing real performance data that has been measured side by side. So there's 2 main tools in the product comparison tools. First is our S parameter viewer. This is great for comparing and overplotting small signal parameters for virtually any part in your signal chain. You can use this to compare either multiple Marki parts side by just dragging and dropping the S parameters that are attached to every single data sheet, or You can drop in S parameter files from other vendors if you want to see how they stack up against the Marki suite. And the second product comparison tool is our performance data viewer. And this one's really powerful. Here's how this one works. Let's say for this example, you want to compare amplifiers. What you do is you go to the performance data viewer and you pick the measurements you care about. So gain, PSAT, IP3, things like that. Then you select which parts from our catalog you want to stack up. You can dial in the test conditions, so you can select temperature, bias voltage, input power, the frequency range that you care about. And this tool is going to automatically generate comparison plots for every part you selected using exactly the conditions you plan on using this part in. Once you have those plots, you can tweak them how you want. So just like any sort of plotting tool, change axes, zoom in, highlight points, that kind of stuff. And then you can export those comparison plots for your proposal or for your design review. It's super fast, super efficient, and it's a great way just to make sure you're choosing the best fit for your specific design goals without the standard method of flipping back and forth between data sheets and filling the gaps yourself. Now, as you know, finding the right part on paper is just the first step, because the obvious next question is, how does this actually behave in your real system? And that there is where our system design and simulation tools come in. So our system design and simulation tools help you understand exactly how your parts are going to behave together in a real system. And this is before you're actually building hardware. One of the tools our applications team uses very often is our spur calculator. This lets you model spurious products in a mixer. It not only predicts where in frequency each spur will land, but it also is going to estimate the suppression level for every single spur generated during any sort of frequency conversion application. The calculator has a couple different views depending on what you're comfortable with or depending on your frequency plan. So you could view it as a CW spectrum analyzer type mode, or you can look at it swept in a sort of a VNA style view. It's not quite a VNA style view, but when we do the live demo, it'll be very clear. This just makes it a flexible tool for analyzing spurs in really any arbitrary frequency plan. It does use an idealized model for a mixer. So if you want fully nonlinear harmonic balance simulations for our mixers and our multipliers, and we're going to actually be re-releasing this soon with some amplifiers and some packaged parts, we do offer a validated PDK that's compatible with Keysight ADS and Cadence Microwave Office. And these models, they capture both small signal and large signal behavior, which is required for devices like mixers. And these aren't models that are tuned to fit datasheet data. These are actual design files for a specific device in the catalog. What that means is when you're simulating, for example, the MM10626H, you're not simulating a generic mixer block that we custom fitted to match the measurement. You are actually simulating that device with those specific diodes and those specific Balun architectures. Essentially, these tools here, the PDK, is the next best thing you can get after sitting in front of a VNA and actually testing hardware. They save a ton of time during the system design. I can't move past this without plugging some previous webinars. So if you're actually looking, if that was interesting to you, and you're looking for best practices for using these models effectively, we've linked another past webinar, which is titled Optimal Simulation Techniques for High Linearity Systems, where I go over exactly how to use the PDK to run high quality simulations. And we do a similar thing. We're going to design a full receiver, and I'll show you in Microwave Office how to run a high quality simulation. That's not necessarily the topic of this webinar. We're going to just show a bit about where they are and how they work. But if you want a deep dive, I suggest exploring the webinar in the sidebar. Now back to the tools. So in addition to the Spur calculator and then the ADS and Microwave Office PDK, we support Keysight System View, which lets you build complete system level simulations, lets you do RF blocks, digital blocks together, lets you explore system level considerations. We support the Monolithics library, which is an industry standard library for high accuracy models for real world RF components. This sort of support makes it easy to drop our parts directly into an existing Monolithics workflow if that's what you're using, if you're using their database for board level or circuit level design. For rapid prototyping, we support the Quantic X microwave building blocks. This is almost like a Lego approach where you can snap together drop-in blocks of Marki components on a prototyping board for very quick, very easy to bring up system level testing. And then lastly, if you're not using any of these platforms for your simulations, we are continually growing this next one, but we do offer fully tabulated datasheet data in Excel files for every single measurement in our datasheet. So every single plot in the datasheet was taken by an engineer at Marki Microwave on a network analyzer. And we exported the data to Excel so that we could plot it for the datasheet. And what we're making available is all the raw data for every plot in every datasheet. This means you're not stuck eyeballing a datasheet curve. You can plug real measured numbers right into your simulation environment. And finally, we've come to our just suite of handy RF utilities and conversion tools. You know, like the little things that save you time and headaches when you need quick answers. So we have simple conversion tables for everyday calculations. So things like direct line insertion loss to coupling for directional couplers, or power to voltage, return loss to VisWAR, frequency to wavelength, all those back and forth types of conversions. Really, the goal of those is just save you some time digging through textbooks or bouncing between random websites every time you need to do a simple conversion. These conversion tables they have those basic ones. We have some more advanced ones like phase noise to jitter, phase noise under vibration, some more advanced ones, all right in your browser. And then to tie all of this together, the entire new Marki Microwave website is designed as its own advanced search tool built for engineers. You can search by part number if you know exactly what you're looking for, or filter by frequency range and product family if you don't. Once you find a part through the advanced search tool that we'll go over in the live demo, once you find it and you're on a product page, you will find virtually everything you need in one place. And I do really mean everything. You select a part, you will see every associated application note, all of the outline drawings. We will give you landing patterns for your PCB, device models, either S parameters or nonlinear, reliability data, material compliance documents, truly everything you might need all in one spot, meaning no more digging around or emailing support for these extra files. They're right there, easy to find. And it's these kinds of everyday tools that we believe just takes the friction out of design work so you can stay focused on the big decisions, not the in-between day-to-day busy work. All right, we are almost done with slides and we're almost ready to jump into the live demo. So we're gonna see these tools in action, but before we do that, let's put some real numbers to this receiver and see exactly how these tools help us design faster. So for this, we're gonna say we're looking at a 20 to 30 gigahertz spectrum hitting our antenna, and we wanna down convert that to a fixed 3 gigahertz IF, and we'll assume a 2 gigahertz bandwidth. So right away, we see we need two filters, a pre-select filter covering that 20 to 30 gigahertz, that's to clean up our front end, and an IF filter covering 2 to 4 gigahertz to select our output band. So let's start by jumping over to the website, and I'm going to show you how we can use the filter search tool to first see what's already in stock is a catalog, a catalog off-the-shelf filter. We will check it against competitor filters with the S parameter viewer tool. Then we will explore how the LC, microstrip, and the mimic design tools can help us close the gap if we don't find the perfect off-the-shelf match. Once we pick the best options for our filters, we're going to circle back here and finish off the rest of the chain. So let's switch gears and go check out the website. We are on the Marki Microwave website, and the first thing we're going to do is we're going to navigate to the page that houses the majority of the tools that we're going to talk about today. And that's under Technical Resources and then Tools. And our first task is to search the catalog for a 20 to 30 gigahertz pre-select filter. And for this, we're going to use the Catalog Filter Search tool. And this allows you to type in filter specs, and it automatically narrows down the massive catalog that we have. We have a pretty familiar style of filter searching and designing interface, where we can type in a lower and an upper cutoff frequency. Optionally, you can specify rejection requirements. So we can request A or require A. This is showing 30 dB rejection at 9 gigahertz, for example. I'm going to turn that off for today's demo. You can select the response you're interested in seeing. You can select the package type you want to see. You can look at all filters at once if you'd like. You can include partial matches. So this would be good if you're looking for something outside of our catalog. You just want to see what's closest. You can do standard chart manipulations. You can change the x-axis and change the y-axis if you'd like. But for today's example, we're going to look at a 20 to 30 gigahertz filter. So 20 gigahertz here and 30 gigahertz here. And we don't want to see low pass, high pass, or reflectionless. We're only going to look at band pass filters today. And for simplicity's sake, let's just say we can accept any package type. This narrowed down the catalog to these three choices. Right now, we're looking at this one, the FB2500. You can see it here in the legend. If we want to look at the next one, we can simply click it. So we see slightly worse roll off on the low side. Another option, significantly more information is being passed on the high side. So it looks like these first two are maybe going to be good for us. What we can do is we can overplot them by selecting multi-select and then just clicking a second plot. We can see the difference. We can hover over and see exactly what is, the loss profile at a given frequency. Same thing with return losses. We can do it here. I think for this example, the closest one we have in the catalog is this FB2500. So right here, we could go to the data sheet if we wanted more information about the part. But I'm going to go ahead and download the S2P file by selecting this. And immediately it pops into our downloads. You can see I've actually downloaded this several times already. And next what we're going to do is I'm going to show you how we can compare this S parameter file with another S parameter file from a competitor's website. And that S parameter file I've already downloaded. I went to their website and I found the closest filter I could for this application and downloaded their S parameters. So if we want to stay here and see how it compares, what we'll do is we'll go to Technical Resources and Tools again. And now we're going to scroll down to the S parameter viewer, which is this tool here. And we have a very simple interface, just an empty plot right now, because we haven't given it any data. To provide data, we can select Choose File. This is going to open up your downloads or wherever you point it to. I've already created a webinar folder, which has the FB2500, the Marki bandpass filter. And also I selected the competitors filter. So I'm going to just select both of them and open. And it immediately overplots them. Down at the bottom, just zoom out a little bit. At the bottom, we can select the data. So if we select, for example, competitors filter, that means these dark lines are the competitor, the dashed lines is the Marki. We can go up here, we can drop markers, we can see exactly what the response is at every point along the way. Just by inspection, it looks like the Marki filter has steeper low side rejections, but the expense is we're actually letting in considerably more information on the low side than the competitor. The competitor is a little bit closer, but it's rolling off this 20 gigahertz point pretty hard. It's providing too much attenuation. So to get the 20 to 30 gigahertz spectrum, I wouldn't say either of these are perfectly ideal. So the next best thing we can do, and this is something that we already talked about, which is the nature of these filters is highly custom. So how does one get a custom filter? Well, traditionally, what one would have to do is they would come to Marki with their filter specs. We would design a filter. We would send you an S parameter file. You would run it through your simulation. And then you come back to us and say, I need the pass band shifted 200 megahertz higher, or whatever the changes that you need. We would change it, resim it, send you new S parameters. We would go back and forth and back and forth. This is no longer how custom filters need to be designed, thanks to our Mimic design tool. And I'm going to show you a quick design right now for a 20 to 30 gigahertz bandpass filter. We're going to go back to Technical Resources and Tools. And now we want to select the Prodigy Filter Designer. But before we do that, now is a good time to just touch on the 3 filter design tools, because we're going to come back and I'm going to do a demo of these 2 as well. The difference between these is that Prodigy truly is a filter design tool. It does full 3D FEM quality filter designs on gas, as in the performance you see out of Prodigy is essentially what you're going to get when we fabricate the filter. The LC filter design tool and the microstrip filter design tool, these are more calculators in that they are running textbook equations in the background and giving you idealized LC values or idealized microstrip layouts. They are still quite useful tools, and they're actually very useful tools at lower frequencies, because at high frequencies, the parasitics begin to dominate, and we no longer are going to get the response we expect using these tools. However, that's where the Prodigy tool comes into play. And at low frequencies, Prodigy does not cover very low frequency filters right now. So these can actually handle low frequency filters to a pretty high degree of accuracy. But let's go ahead and just get started with our 20 to 30 gigahertz filter. And we're going to design a brand new mimic filter. And this is what Prodigy looks like. Again, a very simple interface. We get to select the topology. And in here, these are Marki designs, so they're our own names, and the designer typically gives a little explanation of what it is. So this is a bandpass filter from 20 to 40 gigahertz, center frequencies with 10 to 30% bandwidths. This is a lower frequency at 7 gigahertz, etc. You can select here either typing in or move the slider to your center frequency and your percent bandwidth. You can change the axes if you would like, and you can even set markers. So this is actually already in the spot we want it. We want a minus 3 dB marker because we want to see where our 3 dB rejection is. The X and Y axes are fine for our filter that we're going to be designing. I'm just going to scroll down a little bit. So let's just go ahead and run a design. We're going to need 20 to 30 gigahertz, so that's a 25 gigahertz center frequency with a moderate percent bandwidth. So let's try this khaki high band, because that allows us to be in the sweet spot. Our 25 gigahertz is well within the passband range, and we actually have a lot of bandwidth to sweep, 14 to 40%. So it already set our center frequency to 30, so let's go ahead and drop that to 25. All right. And we see we're at 22 and 27, so we're actually going to broaden this up quite a bit to get our desired passband. And we're almost there. Oh, that's pretty close. 20.9 to 29.2. Can we get a little bit better? All right, let's say we're happy with this filter here. All we'll do is we can hit save your results right here, and you will actually get an S parameter file emailed to you immediately. You can yank that and run that in your simulation. You can submit a quote here. Let's go ahead and let's save our results. It has us fill in this information, and it'll email you the S2P. Let's say you do that and it looks fine. You can submit the RFQ right here, and this gets you in contact with our sales team. This is where you can also say, please improve low side rejection and package into QFN. We'll take this and we will do any sort of tweaks that you want, run a new simulation, and send it back to you. So for this pre-select filter, we're going to go ahead and use this Prodigy filter. Now, what about the IF filter? Well, let's just run a quick example with the other filter design tools. So that's back to technical resources and tools. Now, we're going to be doing a filter from 2 to 4 gigahertz because there's a 3 gigahertz IF with a 2 gigahertz bandwidth. I'm going to do a microstrip filter for this, and that's purely because at 4 gigahertz and at more moderate frequencies like that, I would get a little bit concerned about the parasitics of the inductors and capacitors we're using, because this is like a lumped element design. So let's see what a microstrip design would look like. Select load tool. And we come to another very familiar filter interface where you can select the response, the type, topology, order, etc. I'm going to change the low cutoff to 2 gigahertz or 2000 megahertz, and I'm going to do the same thing on the high side. I'm going to change it to 4 gigahertz or 4000 megahertz. And we can keep the rest of the information the same, and we'll hit compute. And just like that, it's running the calculations in the back end. Gives you the response. So we see some reentrant mode here. We can download S parameters right here, download S2P. And right here we get the information on how to design it. So the resonator dimensions and the layout information. If you wanted to improve this response, one could adjust the order. So as a 5th order, let's just see what a 7th order looks like. Might take just a little bit longer for the calculations in the back to run. But here we go, and we get that nice steep high side rejection here. And we would use something like this. For a filter at this frequency, we could get away with a printed filter using the tool like this. All right, so we've got our filters figured out. Let's go back to the presentation and keep on working through the block diagram. All right, and we're back. Now that we've covered the filters, let's tackle the next piece that's going to make or break a real frequency conversion chain, which is the mixer and LO generation section. If you get this wrong, you end up with unexpected spurs on top of your IF. Essentially, you just degrade dynamic range. So let's start by sanity checking our frequency plan using the spur calculator. I want to make sure I'm not creating spurs that land in my 2 to 4 gigahertz IF band and ensure I'm not jamming adjacent channels. So we're going to actually look outside of our IF range as well and just see what the dynamic range of the entire system will be. So let's see this effect in the spur calculator, and I'm going to show you how to quickly select the optimal mixer for this application as well. Head over to the website. Here we are back at the website. So with the task of validating the frequency plan, the best way to do this is to use the spur calculator. So we'll go back to technical resources and tools. And we're now going to navigate down to here, spur calculator. Now there's 2 different ways of viewing this. There's this, which is like the spur web. Essentially what this is showing is it's showing input frequency on the x-axis and output frequency on the y-axis. And you can see how the spur travels for a swept input. Additionally, it gives you the approximate spurious suppression. So we see the 0L by 3I should be approximately 85 dBc down. You can see our fundamental. We see another spur over here. There's another view, which is the spectrum analyzer view, which is a bit more straightforward, where you're literally looking at a spectrum analyzer. And it gives you on the right-hand side here, when we change the frequency plan around, you'll see the spurs will pop up here. So let's go start with a spur calculator in this web sort of view. I'm going to zoom out just a little bit so we can see the whole thing. All right. So we have options. We can auto update the input or the output frequency, meaning if we're going to be sweeping things, we can have things sweep together. We can show the sum or the difference frequency. And then here's where we actually input our frequencies. So for this, our input is 20 to 30 gigahertz. Our LO is 23 to 33 gigahertz. And our output, it is technically 2 to 4, but we want to make sure we're not crowding up things around us. So I'm going to look between 0 and, I guess, 10. And we can see the effect of sweeping our LO. So we see the spurs that are popping up. These are all here. We can see their approximate suppressions. We can sweep the LO around and see how things change. We can see where everything's intersecting. This is going to be a problem point here, because this means the input and the output frequency of the spurs and the fundamental, which is, oh, I thought it was this one. Oh, it is. Okay. My apologies. So here's the 1 by 1. We can see it's intersecting with a bunch of spurs. So this point here does have crossing spurs that are unable to be filtered out. And we actually see as we move the LO around, that point just moves around. Now, we are sort of fortunate because if we zoom in on our passband of interest, we don't actually get crossing spurs. So now we're only looking at the 2 to 4. And again, this is our fundamental. So we don't actually get anything crossing over the fundamental. It would literally look like an X of another spur over it. But we do have a considerable amount of spurs in our spectrum here. This here, down here, is the calculator options. And we're looking at a low barrier diode. meaning the LO drive requirement's low and the linearity isn't as high as some other options. We can actually change this to a higher barrier diode. It's cut off, but that's an S diode. And we see our spurs are actually improved. Meaning for this frequency plan, we're going to want to have potentially a much higher barrier diode because when we zoom out and we have those crossing spurs, we want to minimize their effect. Now, just for completion's sake, let's just look at this as the spectrum analyzer view. Do the same thing. Our input is 20 gigahertz to 30 gigahertz. Let's click this just to reset, to 20 to start. Our LO is 23 to 33. We'll put this here. And we're going to look, we'll start with our passband and then we'll zoom out. So in our passband, in our 2 to 4, just as the last table showed, we don't have any spurs in the 2 to 4 range. Here I'm actually going to lock the LO and the input together so that when we sweep the input, it sweeps the LO as well. And we see we don't actually introduce spurs into our passband out here. If we look in the extended range, we do get some spurs and we see approximately how high they're going to be and where they're going to be, but they actually don't move around too much and not too much is going to be added. We can change the barrier level and you see some of the spurs go down. I would say this analysis shows me that our frequency plan is not terrible. We do have some spurs that we might need to worry about. We saw in the filter tool that we don't have the best roll off, but I think this is an acceptable frequency plan. So how do we actually find a mixer that gives us a response like this? Well, it's actually quite easy. What we're going to do is we're going to look under, let's say we're looking for surface mount. We're going to go under surface mount, mixers. And this brings up every single surface mount mixer in the catalog. Now I'm just going to type for our RF and LO range. Our low end was 20 and our highest frequency is 33. Our IF range is 2 to 4 gigahertz. And let's say we're designing for optimal IP3 performance. We can simply select IP3 and it reorders them from highest to lowest. And we see our highest linearity option is one of these S diode ones, just as we thought. I'm going to click into this here and go to the product page for this part. So this is the MM1 1850 SSM. Now there's actually a lot going on this page. So we're going to take a minute and just look through. These are the part options. So there's the surface mount and then the evaluation board. But down here under technical resources is a whole bunch of information that is very important for the RF designer. Of course, there's a data sheet, most important. Right here is where you can download drawings. You can get the outline drawing as DXF or DWG. You can get 3D models. You can get the footprint itself. So if you want to know how do I actually put this on my board, this is the footprint that we use on our evaluation board. You could get device models. Now, this is a nonlinear device, so I'll show you this later, but one could get S parameters for different products right here. This says contact us because you can't describe a mixer with S parameters. Every associated application note can be found by just clicking application notes. White papers has the same thing. Reliability information, so if you want the materials compliance documents, you can just select here and you have the entire materials compliance. And all this comes anytime you click into a product page, we give you everything associated with it. And this is actually going to be improving as time goes on. So I would say our frequency plan is validated and we found a really good high linearity candidate mixer. We can look at the data sheet if we'd like. And we'll scroll down. We do see that this does require pretty significant LO drive, 20 to 28 dBm, but the major benefit you get is the IP3 performance. So I would say we select this mixer. Let's go back to the slides now that we've selected filters and mixers and continue on in the design. We're back to the slides. We've sanity checked our frequency plan and we picked a high linearity mixer that covers our RF and our IF bands. The last piece of the frequency conversion is to make sure our LO chain can deliver the power that the mixer needs to hit the spec. In this example, we are generating a 23 to 33 gigahertz LO signal, and we will need a clean driver amplifier that's going to boost the LO to the required power level such that the mixer is turned on fully. We get good conversion loss, we get good spurious performance, and the IP3 performance that we're designing for. So we're going to jump back to the live demo, and I'm going to show you exactly how to select the suitable amplifiers, how to use our performance data viewer to compare performance under your given conditions, compare real options side by side so you can find the best match for your LO path. Once we're done comparing all of the amplifiers and looking at their performance and selecting one, we'll have all the main pieces of our signal chain. We'll have the filters, we'll have the mixer, and the amplifier. And then I'm going to wrap up by showing you how to put it all together for a quick system simulation. Back on the Marki site for the live demo, and now our task is to find candidate amplifiers and use the performance data viewer to compare their performance. So last time we found a mixer, we went right into the package and right into the mixers tab that we wanted. I'm going to show another method of just doing a general search, which is going to be up here in the looking glass. So if we know the part number, we could type it in, but here I just want to see all amplifiers that operate from 20 to 30 gigahertz. I'll go ahead and hit enter. And we get a list of every single amplifier in the catalog, regardless of package, which we can narrow down here, regardless of the amplifier type, which if we want to just look at LNAs or just look at drivers, we do that here. We see every single amplifier from 20 to 30 gigahertz. And down here, we see every single application note that discusses these amplifiers. If we recall, the mixer we needed has a minimum LO drive of 20 dBm. So I'm going to just put 20 for the minimum PSAT. I'm going to show all items, and I'm going to rank this by PSAT. So now we have increasing saturated output power. And we're going to just select a few of these that we're going to use in the performance data viewer. So I think we'll take this one. This is the 7473, AMM 7473. We'll look at this one as well, which is the ADM 8006. And we're going to look at this one too, the AMM 7210. Now I'm going to move over to the performance data viewer, which is here. Now I've actually already plugged all this in. And the reason for that is at the time of doing this, we haven't completed the viewing tool. So there's still some data that's not uploaded yet. So in theory, one would be able to do this exact same sort of analysis for virtually any spec in the data sheet. But right now I'm just looking at gain. We're looking at the 7473, 8007, and the 7210. If we wanted to change the test conditions, we could change it so that we're only looking at a given supply voltage, a given current. We could say we don't want to look at evaluation board data, etc. I'm just going to look at all the data we have. Here's where we can change our axes. So let's say we don't really care what's happening below 0 because we're looking at an amplifier and we're looking at gain. And we also don't really care what's happening out of band. So let's just look at, we're doing 20 to 30. So let's look at like 15 to 35. And this is measured gain for all of the amplifiers. We have the key here to decode what we're looking at. But already it's very clear that this amplifier, the 8007, is likely going to be the one that we select for this application. You can turn on and off some of them. So like if I want to just turn off some of these lower powered ones or lower gain options, because those aren't going to be it. I could turn off this guy here, or maybe I keep that one on, I'll turn this one off. And we can take this, we can save the SVG. So we can save the image itself. Clicking there, it gets downloaded here. You can now take this and put this in your design review slides if you'd like. But using the performance data viewer, I think we would select the ADM 8007 for this amplifier slot. So we're going to go back to the slides and complete our design. All right, we're back. We've got our mixers, we've got our filters, and our LO chain all lined up. And you would tackle the rest of the blocks like the limiter, the LNA, the balun or differential amp, however you want to implement that. You would tackle those the exact same way. You'd use the proper search tool to find parts that meet your specs. You'd compare real data with either the S parameter viewer or the performance data viewer, depending on which applies. And then you'd pick what works best for your design goals. So at this point, you've got candidate parts. You've got parts that on paper look like they are going to work for this application. So the last step is to see how they'll actually behave together in your real system. That is where our system modeling and simulation tools come in. Let's take a look at where we can find these. and how you can use them to tie this all together and check your design before you ever build hardware. So let's get back to the live demo and look at the website. Okay, and we are almost done with our design. We're back on the website. We've selected filters or designed filters. We've selected a mixer that gives us sufficient linearity for spurious suppression and IP3. We've compared some amplifiers. Now we're at the point that we want to run some real simulations. Now, how do we do that? We're going to go back to technical resources, only now, instead of going to tools, we're going to do device models. Now, this is where we're going to have all of our device models. ADS and Microwave Office, these can be downloaded down here as well if you want just the ADS or just the Microwave Office. These are our fully nonlinear models. So these, you download them and you load them into your workspace in the software that you're using, and you are actually simulating specific devices. This is where we're doing harmonic balance simulations of a real mixer. In our case, we selected the MM1 1850S. The model in the PDK is not a generic mixer model that's been fitted to the data. It truly is modeling the MM1 1850S. Additionally, you can access system view, Monolithics, Quantic, the X microwave blocks, and complete set of S parameters. Additionally, there's the performance data. So here's where we can hit download on the performance data, and we actually get, this is an example of an amplifier, but we actually get an Excel file. Well, I'm going to pull it onto that screen in 1 second. We actually get this CSV file that contains all the data in the data sheet for a given part. Meaning, if you are doing some system level modeling and you aren't using ADS or Microwave Office, you're not using any of these, we will still offer you tabulated data to do any sort of system simulations you would need. And if you see, there's still a few that are in the backlog that need to be inputted. And I do mean there's a lot. So showing all items, there's almost 700 products to be modeled. Now, if there's ever a product where you don't have this software, you're not using any of these tools, you don't see performance data, do not hesitate to email the support at Marki Microwave email group, and we're happy to gather the data for you and send it your way. But this is where you're going to find the best models possible for Marki parts. We're going to go back to the slides, and I'm going to show a couple of Microwave Office simulation results just so you can gain confidence in the quality of the models here. So we're going to go back to the slides now. Now we're back at the slides, and we have another webinar where we talked about how to use those simulation tools to design receivers. And I actually took the next couple slides from that webinar. And this is just showing you the types of agreement one can get between the simulation tools and a measured value. So on the left, I'm showing a measurement of a given mixer, and on the right is what you get out of a Microwave Office simulation using the models we were just going over. So we see conversion loss is simulated to a high degree of accuracy, isolations as well, even really low powered things. So the spurious suppression or the spurious loss, we're seeing a great degree of accuracy. Linearity, like IP3, same deal. So I'm going to wrap up the webinar. Before we do, we're just going to hit the key takeaways one more time, and we can open up to some questions and conclusions. So first, we saw how the filter search and the filter design tools help you quickly find either off-the-shelf options or help you quickly build custom solutions without burying your head in data sheets for a day. Second, you've seen how our product comparison tools let you overlay real performance data side by side so you can be confident in your part selection, both S parameter viewing tools as well as true performance data. So that's the under your given conditions and looking at more than just small signal data. Third, you've seen how our system design and simulation tools can help you anticipate how parts will interact, catch surprises early, and plan your frequency conversion chain with confidence. And finally, you've seen how our handy RF utilities and advanced search features just take the friction out of everyday design work and help you get what you need faster. So together, the tools we discussed today are just here to help speed up your design flow, help you make smarter decisions, and really to help you stay focused on solving real engineering problems, not just getting lost in the busy work. So I encourage you to jump on the website and try these out for yourself. These are live on the Marki website, totally free to use. And of course, if you have questions, if you want help getting started, or if you just want to talk to me about the tools a little bit more, reach out to me or the applications engineering team anytime. That is exactly what we're here for. You can email us at support@markimicrowave.com. You can give us a call. Phone number's on the website, and I'll pick up and I'll chat with you as long as you want to chat about the tools, or other Marki parts. So with that, thank you all for your time today. I'll stick around for any questions that you might have.
All right, Harley, thank you so much for that great presentation and all the demos. So we do have a couple minutes for Q&A, about 8 minutes. So for our audience members, if you do ask a question, we might not get to it. So we will get back to most of you following today's webinar. All right, Harley, so let's get right to it. This first question, do I need to register with Marki to use the tools? How do I get the Prodigy SP2 without registering?
So the Prodigy filter designer is free to use. No need to register anything with an email if you just want to see filter results. However, in order to receive the S2P file, you do give us your email and we'll email you the S2P. But you don't need to make an account or anything. So if you just want to simulate what's possible in the filter design space, you can log into Prodigy and simulate all day if you'd like. And it's not until you want to download the S2P that you give us any information.
All right, thank you so much for that answer. So next one here in our queue, if my frequency plan or spec isn't covered by your standard parts in the search, can I request a custom design through the tools beyond just filters?
So for custom filters is easy through Prodigy. No, so we don't actually have like a custom mixer designer or custom amplifier designer. However, if there is a part that you'd like to see that isn't currently in our catalog, you can feel free to either email support, so support@Marki Microwave, and we could do a first pass look as to whether we could develop something, or you could contact your local sales manager, and they'll go up the design chain themselves. However, easiest is probably just to email support. You can give us a list of specs you want to see, and then we'll flow it over to the design team.
All right, Harley, who do I contact if I want help running a simulation?
So for simulation help, that's also going to be support. And what we'll do is there's a couple different ways that we can go about simulation help. You could either send us, attach your simulation workspace when emailing the support@Marki Microwave email box. So that'll go to me and the team. We'll be able to open up your workspace and debug it. And, if there's issues, we can just fix it and send it right back to you. Alternatively, if you want to do a live help session, I guess, you can, so the same email address, and what we'll do is we'll just schedule a video call with you, and you and I can hop on and debug together. And then again, there should be linked here, there's another webinar where we go over all the most common simulations. So you can always use that as a resource, but if you want to talk to me, just go ahead and email support, and I'm happy to help you out with your simulations.
Great, thank you so much for that answer. Okay, next one here. How often do you update the catalog and models?
Catalog's updated fairly frequently. So if you're on the website under any of the surface mount connectorized bare die headers, at the bottom is the online catalog, and that's kept up to date. The actual harmonic balance models, we have an update coming out before the end of the year, which is going to include some new parts, update some part numbers, but it's not something that we update on a weekly or monthly basis, because it's a more involved project than updating the catalog, but the catalog is always going to be up to date.
So Harley, next one here. What's the difference between the spur calculator and just doing a harmonic balance sim?
The spur calculator is a calculator, so it's taking a mathematical model of a ideal mixer. It's not an actual simulation. It's truly is a calculator. So it gives you theoretical like suppressions and gives you ideas of where spurs are going to land, but it's not going to give you a swept measurement. Like it won't actually show you what the spur is going to look like across frequency for a specific mixer in a specific frequency plan. The only way to do that, where you want to see your frequency plan and you want to actually see a specific mixer's performance, that's where the harmonic balance simulations come into play, where you can take like what we showed in the slides, where you can take a specific mixer and show its exact performance. So for a more realistic look at to how a part's going to perform, you're going to want to use the harmonic balance simulation. But if you just want a quick high-level look, like frequency plan validation is a super common use for the spur calculator, you would use that tool. And that's actually something we do all the time in support, where people will send us their frequency plan and just ask us to characterize the spurs. And typically what we do is we'll plug it into the spur calculator, and that's just our first pass just to see where the spurs are, which ones are likely going to be trouble, and then we go into lab and we know exactly which ones to characterize. So that's kind of like the main difference between the two and when you would use one versus the other.
So Harley, we're going to grab this last one here.
Yep.
How accurate are the filter design tools compared to real measured data?
The Prodigy tools are extremely accurate. I wish I had included a slide, but if you want to see, please email support and I'll send you some measured data. The results from Prodigy, since that's an actual mimic design tool, and it's doing full like FEM quality filters, the performance virtually overlaps within a fraction, like 0.1, 0.2 dB variation from what you're seeing in the simulation to what you're actually going to measure. The LC and the microstrip tools are more similar to the spur calculator, where they are calculators. They give ideal component values, ideal layouts. If you look closely at like the LC filter designer, you'll see things like 12.263 picofarads. So you're not actually going to find a capacitor with that value. So those tend to drift a little bit just based on what parts are available to you. And then also at higher frequencies, the parasitics of the lumped L's and C's, or even of the microstrip, begin to dominate, and you don't see as close of agreement between what you see in the tool and what you would see in a network analyzer. So the LC and the microstrip are good for low frequency and just seeing the design space of a filter, whereas Prodigy is actually extremely accurate to what you're going to get in hardware.
Right. Harley, thank you so much for that last answer. Perfect timing. We are right at the top of the hour.
Perfect.
So we are going to start to wrap things up right now. So I want to say, Harley, thank you so much for such a great presentation and for handling a few of our attendees' questions. So thank you for being here.
Sure. Thanks for having me.
And thank you to our audience members for being here today. All right, everybody, thanks so much, and I'll talk to you soon.